talk, 5 minutes question, and
okay. Okay. Hello, everyone. I'm Cristian Carvajal. I'm a PhD student at LAM in Marseille. I'm sorry for those issues. I hope you didn't read anything. I'm working in a stochastic star formation history at high redshift. So let's start. Fortunately, we already talked a lot about the excess of UV bright galaxies at high redshift that we can see from the UV luminosity function. But let's go into through it a bit fast. So maybe also you cannot see properly. But okay, from the UV luminosity function, we have an excess of UV bright galaxies that we were not expecting at all. And there are already some possible explanation of this as a high star formation efficiency, a top-heavy initial mass function, a stochastic star formation history, evolution in the data duration, between others that also have been proposed. And I know that there are already, we hear a lot about the possibility of the stochastic star formation as being a possible solution, as a spoiler, but let's keep that in mind as the main point of this presentation. So there is with the UV luminosity function, we are measuring the underlying halo mass distribution, and there is a relation between the halo mass and the UV luminosity. This relation is not one-to-one, it's not linear, so rather than that, we have a distribution of UV luminosity at a given halo mass. And this distribution is given by sigma UV, that is the width or the scatter of the distribution. If we go to lower halos, this is higher, okay? And as you know, we expect to be dominated by lower mass halos at high redshift. So we expect this value to be higher at high redshift. One natural way to explain this is with a Barsi or a stochastic SFH. That is not, if we take the star formation rate and we have it as a function of time, we will not have something smooth, but rather than that, it's dominated by periods with high star formation rate or high star formation activity, and also with periods with low star formation activity. And this is because the gravitational potential is not deep enough to withstand the supernova and the radioactive feedback, okay? However, there are many effects that could play a role here. So in this way, we will enlarge these distributions. So we will have that faint galaxies will look bright. So we will flat a little bit the UV luminosity function, so we could explain this excess. How we can check if this is possible or if we have this at high redshift? So for that, we are modeling the star formation history with two components. One of them is just the baseline, and we add a stochastic component that adds some fluctuations in the baseline. For now, we are taking as baseline a tau delayed model that all of you know very well. And the stochastic component we are doing through a power spectral density that is just something in Fourier that is adding some scatter in the baseline. And we are doing this for different time scales. Okay, so we have 3 parameters, tau break that tell us the time scale where the events are no longer correlated, alpha that is the power of the high frequency, that means small time scales, and sigma that tell us how what is the amplitude of the burst, right? So if we plug these two things and we take the star formation history for different values of sigma, going from something really a small fluctuation to something higher, we have something like this. The first one, we have just the delay model, that is what we know, right? And if we increase a little bit more, we will have an SFH completely dominated by burst. So we took this and we put it in Seagull, that I know now you know perfectly and you can do a lot of SED fitting, right? So we included as the star formation history model, okay? And the first thing that we did is doing some simulated catalogs in order to see if we can recover the parameter space of the observation at high redshift for different, okay, for different values of sigma. So we took this approach and we are doing some SED fitting in JWST. That is a survey that includes photometric measurement and also some spectroscopy information. And we are doing for high redshift galaxies between 6 and 12. For now, we are using photometry medium but narrow bands, and some selection effects. Okay, let's go a bit faster. So what we are doing in order to see if the galaxies are stochastic or bursty or not is taking different kind of SFH, going from something smooth to something more bursty, and we fit our galaxies. Here you can see one of those examples for one galaxy where these squared are the observation, and we have the different SFH model. And you can see that the black one doesn't really reproduce the observation, but if we add some more burstiness, it is a bit better, right? This naturally impact a little bit the properties of the galaxies. And for example, here we have the main sequence, that is the star formation rate with the stellar mass. Okay? So what is important here, we have our 3 redshift beams, and what is important is that you can see the different SFH. And if we have something smooth, an SFH smooth, we have a tight correlation in all the redshift beams. That is something that we will not expect at high redshift. Naturally, if we have something more bursty, we have more scatter. So this tells us that the model that you assume as an SFH really impact, in this case, the main sequence. Now, the galaxies are stochastic or not. So we did a classification based on the bias factor that allow us to compare different models. Okay? And in case of this factor is bigger than 3, we consider as a bursty galaxy. And here you can see the fraction of bursty galaxies as function of the redshift, and we see an increase with the redshift that also have been observed for other observational work with a different kind of SFH modeling. We also try other tracers of burstiness as the recent star formation rate, at the rate of the recent star formation rate and the star formation in the last 100 megayears. And here we have our 3 population loop. So we have this galaxies classified as smooth that slightly decrease with decreasing redshift, and we have our bursty galaxies with a positive ratio that they have a median ratio of around 0.5, and also we saw some galaxies with a negative ratio. That means that there are some galaxies that have a decreasing star formation activity. And it's important to mention that this agrees with other spectroscopy surveys. We also checked sigma UV, that is what took us up to this point. And remember, please, that is the scatter in the halo mass and the UV magnitude relation. And we measure it from the magnitude distribution. And what you can see at the beginning is that there is a slightly decreasing, right? However, these are consistent with other measurements. But the most important point here is that this level of stochasticity or sigma UV is not enough to be able to explain the overabundance of bright galaxies at high redshift, as they should be around 1.5 or even greater. So this means that there are other factors that are having an important role here to be able to explain this. So for that, we also try with the star formation efficiency, and it's a bit difficult to get. So for that, we assume an stellar to halo mass relation in order to be able to estimate the halo mass for our stellar mass that come from the SSD modeling, assuming the stellar to halo mass relation, and we found this thing that you can see here, maybe not that clear, but they agree with other measurements from the literature. However, it's still too little to be able to explain together with sigma UV this overabundance of bright galaxies at high redshift. So this means that, again, there is another important effect that we are not really considering here right now to explain this overabundance of bright UV galaxies at high redshift. So I leave you here with my conclusion, and if you want to see more details, please cite me. Thank you.
Question? People are exhausted now, so thank you. If you have questions.
simply rocket, and this.
It is our exercise for students to present 10 minutes talk, 5 minutes question, but we cannot do better. Otherwise, we spend all night. But actually,
And this like
Okay.
close to. Yes.
Okay. And then, is it on?
No. I think that.
Oh, okay.